always assume that it is bounded, which is not necessary, but makes life easier. What makes also life easier is that we have something that one would call a kernel in the continuous case. That is, we can make sense out of A of m. That means just I apply A to the Dirac, to the conical Dirac, if you want, and take the scalar product with delta n. And what's nice is that in this space, delta n is just a true function, which is not, of course, in the continuous case. Okay. One thing that I will use frequently is the kernel of the resultant of the operator h, which I usually call g for Green's function, and it's just this. Here is a warm-up about the solutions of the Schrödinger equation. Suppose we have a solution which is in L2, then of course E is an eigenvalue and it belongs to the spectrum, and by definition it belongs to the pure points part of the spectrum of the operator. Is a warning, the set E naught, by this I mean the set of all proper eigenvalues, that is L2 eigenvalues. This set of is countable because we are working on a separable Hilbert space, but the pure point spectrum, which is the closure of E naught, can very well be an interval, right? Because this set E naught might be dense in some intervals or everywhere. Yeah, here's one trivial example. What always helps me to think about that. Suppose you take the function lowercase r on the lattice, and since the rational numbers are countable, we can let r of n run through all the rational numbers with 0 and 1. Right. Then we look at the operator capital R, which is just multiplication by lowercase r, and this operator has eigenvalues which are just the rational numbers in 0, 1, but the pure point spectrum is the whole interval, because this set, of course, is dense. More interesting, prominent example for pure point spectrum that is thick in this sense are random Schrödinger operators. For example, you have the omega independent, identically distributed random variables. They have, in many cases, pure point spectrum either at the boundary of the spectrum or everywhere. Okay. Pardon me? Well, E0 is the set of eigenvalues, and this is countable, right? Okay, here are the physical and non-physical eigenvalues of my physics professor. We call the function a generalized eigenfunction. If it solves the Schrödinger equation, it solves it in the sense of here finite difference operators or differential operators, and is not growing too much. So I want that U of n can be bounded by a polynomial. And this set I call E, this paragraphic E. And what is known since the 50s is Schnoll's theorem that says that each generalized eigenvalue, this is E, belongs to the spectrum. Moreover, the generalized eigenvalues are dense in the spectrum, and they give a set of full spectral measures. So this, in a sense, answers or clears the confusion I had in my. Pardon me? Well, there are no eigenspaces. I mean, for E0 you have eigenspaces, right? But for generalized eigenfunctions, orthogonal what's not. In fact, the typical thing is that you have a whole continuum of generalized eigenvalues, right? For example, here in this case, for the free operator, you have for every E in every non-negative E, you have a solution, right? So it's a continuous set of solutions. There is no, you cannot make sense out of the word of orthogonal. Okay, here are two open questions concerning this. You see, why should we have polynomially bounded functions? Why not bounded? And actually, I think in all bounded eigenfunctions would be enough. But in general, it's not known. It would be interesting to know whether bounded eigensolutions would be sufficient to determine this one. But that's not the question. Another open question is what can be said about the spectral type. I already mentioned that one might hope that non-L2 solutions give rise to a continuous spectrum, but also that is not known except for very special cases. Pardon me? Bounded. I mean, it's pointwise bounded. Again, I of t, which is e to the minus I th psi, where that means I solve what's also known as the time-dependent Schrödinger equation with initial state psi, and then the solution is this psi t e to the minus I th. E to the minus ITH is defined through the functional calculus or spectral theorem, whatever you want to call it. But actually, in our case, it can also be defined by a power series because we have bounded operators. So here is an example what we can read off from eigenvalue equations. Suppose we have a true eigenvalue. So h psi is lambda psi is in the 2. Then this is the time evolution, and obviously this is very, if you want, boring because it just adds an oscillating factor to the psi. For example, the probability to find the particle somewhere is independent of t because this probability is just the absolute square of this, and then the e to the minus it lambda simply drops out. Now suppose that psi is in the absolutely continuous subspace of your operator. That means, back to the back measure, right? Then you can compute this, and it's just the Fourier transform of h psi. But the Fourier transform of an L1 function goes to 0, which is well known, right? So it means that pure point spectrum, or at least the set of L2 eigenvalues, and the AC part of the spectrum behave completely different under e to the minus ith. So here is an object that measures this to some extent. So what you do here is you take a function, a capital phi that is non-negative, say. Here you have your psi, you let it evolve. Then you multiply by your function capital phi, and then you let it evolve it backwards, and you take the scalar function psi. So that is kind of average time evolution of this observable phi effect. That is something that physicists are interested in, and I will give you a few examples of capital phi that we will see here. Of course, this also can be restricted to part of the spectrum by taking a spectral projection. Everything is this. Okay, here is the famous Rage theorem, Rage after Ruel, Hagmon, Giorgescu, and Enz. This is coined by Barry Simon, who likes to use fancy names for theorems. And it says the following. Take the time evolution average with capital phi equal to the characteristic function of k. That is, this function is 1 if n is in the set k and it's 0 otherwise. Then this is my, this relatively simple expression is my complicated n part here. And then the Rage theorem says that this goes to 0 if and only if psi is in the continuous subspace. Moreover, if psi is in the pure point subspace, then n phi t is bounded away from 0. So this is a theorem that actually characterizes continuous versus pure point spectrum. Most of the time, I will use, and I would say physicists use, capital phi of n to be n to the p. So n is this is essentially n to the p, except that I want it differentiable at the origin, so it's 1 plus n squared with the square root of this. So this quantity tells you how much the particle spreads in terms of the polynomial n to the p. Right? If this is growing, then it means the particle will move out more and more. And if this is bounded, then it means the particle will stay essentially where it was. And it's relatively easy to see if you are in the continuous spectrum, in the continuous subset, then this quantity will go to infinity. And if it's bounded, then psi is infinity. Unfortunately, this is not an if and only. So you can have this going to infinity, but psi is not in the continuous subspace, and you can have this unbounded even if psi is in infinity. So here's a bit of terminology. If for all polynomials MP of Ti is bounded, then you say that you have dynamical localization in the I. That means if you take a particle with inside I, then it will in time evolution it will not grow infinity in the sense that all the polynomials will say that it stays essentially stays bounded. While we say that we have dynamical delocalization if that is not true. That is, if for some t we have MP of t going to infinity, that is, the particle somehow leaves each finite region. What? Oh. Oh yeah. I'm sorry. Yeah, that is a vital. There should be MT comma E. What? MPTI, yeah. Yeah, that's it. Okay, what is known about dynamical localization and delocalization? Well, for the Anderson model, that is, you have independent identically distributed Random variables with some condition like bounded density of the distribution. Then we know that for dimension E equal 1, at every energy you have dynamical localization. And recall, dynamical localization is stronger than spectral localization. That is, we not only have pure point spectrum, but we have localization in this somewhat stronger sense. And for E bigger than 1, we know that for strongest order or at extreme energies, we also have dynamical localization. Now what about dynamical delocalization? Well, the first example is if the operator is absolutely continuous, saying with periodic potential, then you have dynamical delocalization. Then there is an example by Jitomierskaya, Schulz, Baldes, and Stolz in dimension B equal 1. Namely, the random polymer model at special energies has dynamical delocalization. I just recall that Peter Hislop was talking about this model and this work together with Professor Nakano. And there is one more surprising, interesting example, that is the random Landau model. That is, you have a restriction operator with a constant magnetic field. Then Gemini, Klein, and Schenker proved that there is some dynamical delocalization. Actually, they need the P, that is the power, is like 22 or so. Oh, that's right. Yeah, that's right. Yes, that's right. So, what Professor Nakano said actually is, if I really take MPT with let's say R here, then it says there is localization somewhere, and you don't know where. Thanks. So here is our result that looks very technical, but I think is very useful. Suppose you have you have a set of generalized eigenvalues, and the eigenfunctions are called CE. And this E is in a set I, not necessarily an interval, of positive Lebesgue matching. Right? So it's not enough to have, let's say, a countable number of energies, but we really need a whole continuum of eigenvalues such that, think of this, let's suppose the CI are bounded, then this can be dropped, so you just need to have a condition on P here. Otherwise, we have more concrete examples. If psi might even grow, right? It's not allowed to grow more than polynomially, but then in any way this cannot be finite. Then NP of T, and this now is NP of T and R, is essentially bigger than T. But this I mean it's bigger than constant times T to the 1 minus epsilon, and for every epsilon there is such a constant. Especially if psi is bounded, then we have dynamical localization for T bigger than E minus 1. This does not quite follow from this, but is an extension of this. Right. If you just use this, then you will get it for P bigger than D, because then 1 over n to the D is n to the D plus something. It's has a finite sign. Not example. That is actually our starting point. Suppose you have what is called a trimmed Hamiltonian. That means you take a set gamma, might be any set for the beginning, and you suppose that V lives only on gamma, in the sense that V of n is 0 if n is not in gamma. Right. So this is called a gamma trimmed Hamiltonian. And in the special case I consider here, I just take a sublattice. Right. Gamma is just a product, a Cartesian product of V, but at least one of these V's get a P in front which is bigger than 1. So I'll show you a picture in a second. So here it is. This is 2z times z. So in black you see the lattice, and blue are the points where the potential can be non-zero. The point is that the potential has to be 0 on these lines. And actually I do not really insist on the potential being non-zero here. I just want the potential to be 0 here, so the picture could look like this. But it might be 0 here as well. And so on. Now, if you look from the physics point of view, you might think that because you have these long strips here going out to plus and minus infinity, that you have some kind of continuous spectrum here. To end the story, I can prove that. But That is more or less the particle should be able to move out at least at certain energies to let the plus infinity in this system. Actually, Krishna and I can prove if you take only a finite part in this direction and wrap it around to a cylinder, then you have continuous spectrum. The particle goes out to infinity in the sense of continuous spectrum. Okay. Now, why is that interesting? Well, I think it's interesting because if I restrict the operator H if I restrict the operator to 2 of gamma C, that is the what I would call the non-active sites, that is where the potential certainly is 0. You look at the spectrum of this operator. Right? Now, if you have a gamma trimmed operator, then there is dynamical delocalization in sigma. The particle goes out, at least in the average sense. And what I'd like to emphasize is that it has nothing to do with the behavior of V on set gamma. Could be anything, could be 0 there as well. Right? Okay. Now here's the result again. That is this complicated object goes to infinity. Again, I have no I here, but if I insert I, this is still true. This is still true because if I'm in this set, in the spectrum of the restricted operator. Now, here is the very simple proof. You just define your function psi, which is an eigenfunction, right? Why is it an eigenfunction? Well, here it's the free operator, that's fine. Here it's also an eigenfunction of the free operator, but you see that this function actually is 0 on gamma, on this sublattice gamma. That means that this function has no idea what happens on gamma, and it is an eigenfunction of the free operator and also of the of the non-free operator. So this is the solution, and then you apply the theorem that I just did. Okay. Now, let's look at a more specific model, namely, let's take gamma as we had it. But now we say something about the operator, the potential on gamma. We want it to be random, IID, random variables, except that outside gamma we put it 0, right? So this is known as the gamma-trimmed Anderson model, or I prefer the expression Anderson model with missing sides. Now, as we have seen, there is dynamical. One can prove that there is dynamical localization for small energies. Here is again a mistake that should be 2 cosine pi over p1. Anyway, for small energies and we have opportunity for big energies, there is dynamical localization. And when you try to prove dynamical localization for E bigger than, again, 2 cosine pi over p1, the problem is that you cannot prove the Wigner estimate, which is usually essential for proofs of dynamical localization or even spectral localization. So. Now that this can be done, that for small energies you prove a Wigner estimate, and here are a number of references for the dynamical localization. Now, but we know there is also dynamical delocalization. There's dynamical delocalization in the other region, that is when the spectrum is bigger than 2 cosine pi over p1. And that means that we have, I think it's the first model where we have the region with dynamical localization and another region with dynamical delocalization. Okay. I think I have time to spend a few remarks on the proof. So first of all, what we do is it's easier to use this kind of averaging. Remember, before we had here 0 to t, and there was no e to the minus t over t. This is another way to average, and it doesn't give too much of an error. But this means it can be bounded by t to the epsilon for any epsilon. And then the next thing we use, and that is the reason why we introduce this averaging process, we can reduce this one to estimates on the resolvent, and at least for me, it's much easier to estimate resolvents than oscillating to the ITH. This most this is just look closely at the literature and computers. So here comes the main, I think, very simple idea. Suppose we have an operator h psi with an operator h with eigenfunction psi and eigenvector and eigenvalue e, and I want that psi of 0 is not 0, which is not much of a restriction, of course. Then I simply write the Schrödinger equation again, except that I add this term which makes this invertible, right? That is the idea. Then you invert, and then you estimate, and then you estimate again, and then you have essentially the result on the bottom. So I think that's a very easy idea, except that of course it's wrong. What is wrong? Well, wrong. All this is true for a 2 eigenfunction, right? But we are just interested in eigenfunctions psi that are not L2. Therefore, we do not know what it means to apply the resolvent to psi. Well, of course, you can hope that it's essentially this, but that is something we have to prove, and the essential tool we use for this is the Thomas estimate that says that that the resolvent for z, which is not real, can be estimated in this way, that is the case exponential. More precisely, outside the spectrum, the resolvents decay exponentially, and that is very, very general theory. like Count Thomas and many other people who work on it. So here is the result again. Here is some extension of the result which gives which allows you to take smaller p in some cases. You remember perhaps that I had p minus 1 versus the p of. So at the end, I would like to come to what I think is the most interesting example. This time it's not only interesting but also complicated, because first of all we start on R3, so we have to do all the theory I did before for the continuous case, but that can be done. And this time the potential is a bit awkward, namely it's a delta potential in 3 dimensions. So somehow that means that the potential is only acting at the lattice points. Somehow if the particle is there, it gets hit by the potential, but outside the lattice nothing is happening. That sounds easy, but in 3 dimensions it's not so easy to define this operator really. In fact, in 1 dimension it's relatively easy, in 2 and 3 it's relatively complicated, and in 4 it's not possible. That is, point interactions can only be defined in dimension up to 3. How do we do it? If you're not familiar with this, just take it as something. Let me just remark there are several ways to define the delta interaction. One is by theory of self-adjoint extensions. That is, you look at the operator on L2 of R3 minus the lattice Z3. There it's of course just the minus Laplace operator. Minus Laplace operator on that set is not self-adjoint. In dimension 4 it is self-adjoint, but in dimension 3 it's not self-adjoint, and you have various self-adjoint extensions, and the delta is one of the. In fact, you have a one parameter. Yeah, thanks. You have a one parameter family of self-adjoint extensions. Okay, and then you can approximate by regular potentials, and you can even use non-standard analysis. So the approximation of regular potentials is also a bit awkward. Just let me tell you it's not what you probably believe it should be. This potential has not a one norm constant, but it has a decreasing L1 norm, and moreover it has only a limit if there is a lambda not such a. This is true, and in fact that is called zero energy resonance, and that is the bridge to Professor Zina's talk, who was talking about resonances. Anyway, our definition is just we take from the book of Alvedero, Cohn, Gestesi, and Holden the expression for the resolvent of the point interaction operator, and that is the expression. And what you can see from this is the resolvent kernel for the point interaction is the free operator kernel plus something that is somewhat using the resolvent equation in a naive way, except that this gamma is a infinite matrix which has these entries. So, and then you have to take the inverse and so on. So it's still very complicated. But here is the results we have. In an old paper by Hislop, Krishna, and myself, we proved that the random version of the delta operator has pure point spectrum, and in fact dynamical localization near the bottom of the spectrum. The bottom of the spectrum, so the spectrum looks like there is an interval, E0 to E1, and then there is a second band E2 to infinity. Sometimes they can overlap, but sometimes they don't, and we proved some localization here. Now, with the method used here, we find again solutions that are zero on the points, and therefore we can employ our theorem saying that there is dynamical delocalization for n that is e bigger than pi squared. So that means, so let me just say that the machinery works for has to be extended, and what was especially a problem was that the Thomas estimate was not known for point interactions. We had to prove that ourselves, and it took us quite some time. Okay. Thank you very much for your attention.
Thank you so much. So, here is the time for discussion or question. Yes, please.
Warner, could you show the first few slides when you were talking about the probability of the probability of?
You say stop, okay?
Yes. At the very beginning.
Very beginning.
Yes.
Oh.
After you talked about your teacher. Yes. No, before you introduced there. Yeah, before the model. Yeah. Okay. Right. After that. Yes. Then you had a theorem. If it goes to if it is in the absolutely continuous spectrum, goes to zero.
Yeah.
Riemann-Lebesgue lemma, that is just some idea. Now, there is a partial converse to that.
What?
There is a partial converse to that. If psi is in absolutely continuous spectral subspace, then that probability goes to zero. Okay.
Yeah.
But if that probability goes to zero in a certain rate, then the vector has to be in absolutely continuous spectral subspace.
Yes.
Namely, that probability, if it is square integrable in T,
Yes.
that proves that the vector has to be an absolutely continuous vector.
Yes.
So a partial converse is known.
That is true. That is true. Thank you very much for this remark. In fact, there are a lot of words about this and various types of transient AC spectrum, recurrent AC spectrum. Yeah. Thank you very much.
Are there any questions? I have just one question. For the delta interaction result, what about the two dimensions?
Oh, yeah. We believe that we can do the same in 2 dimensions. The problem is that the Green's function looks a bit awkward there because you have to deal with Hankel functions and things like that. But we think we can do it. But it's again the Thomas estimate that one has to do. But you know, we think we have the result.
So that
this is probably wrong. At least it's wrong in the sense that we don't have dynamical localization. Now it might be that we still have spectral localization while having dynamic delocalization, but I don't believe that. But it's not, I mean, you cannot do really with it.
Are there any questions?
Thank you, sir. I invite the chair to present a token of appreciation to the speaker. For the next session, I invite Professor Werner Kirsch, University of Hagen, Germany, to introduce the speaker, Geetika Sebastian.
Thank you. So it's a pleasure to announce Professor Geetika Sebastian. So she is an assistant professor at the Department of Mathematics at the National Institute of Technology at Connecticut. She did her bachelor's at St. Stephen's College, University of Delhi, then master at the IIT Guwahati, and her PhD at Hyderabad in 2018. The research focuses on functional analysis, particularly Banach algebras and invertible elements. Before joining NIT Connecticut, she worked as a visiting scientist at IDI Bangalore and had a postdoctoral fellowship at IICH at Bangalore. Please, thank you.
Thank you, sir, for the introduction. I thank the organizers to give me this opportunity. If you've heard me talking on this topic before, so please bear with me. Others, if you could occupy the front seat, because I will use the board a lot. So if you will not be able to use the board, see the board if you are sitting behind. Okay. So the title of my talk today is a multiplicative spectral criterion for characters on a C-star array. So this is joint work with Professor Rudy Britz and Sheikh Toon from Johannesburg. Let me just start with fixing the notation. So A stands for a complex unital Banach algebra. The identity in the Banach algebra of the unit element will be denoted by bold 1. G of A denotes a set of all invertible elements in the Banach algebra. G1 of A is the connected component of G of A containing the identity element. So let me just spend 5 minutes on explaining G1 of A because we are going to use that a bit extensively. So by definition of A, G1 of A is the connected component of G of A. Written here, it is equal to the set EXA, which contains the finite product of elements in the Banach algebra. Okay, so it is easy for you to see. So I have to show that EXP of A is equal to G1 of A. You can see that any element in EXP of A is invertible. So EXP of A is a subset of G of A. If I can show that any element in EXP of A is connected to the identity with the path, then that means EXP of A will be a subset of G1 of A. So how do I connect an element in EXP of A to the identity? It's simple. So take EX2 to EXN. This is a typical element in EXP of A. I define the path from 0, 1 to G of A as gamma of t is equal to e raised power t x1, e raised power t x2 to e raised power t xn. One can see that gamma of 1 is this element itself and gamma of 0 is identity. So every element in EXP of A is connected to the identity, hence EXP of A is sitting inside G of A. Now I have to show that if you want to show that EXP of A is equal to G of A, G1 of A, then what you have to do is show that EXP of A is both open and closed in G of A. And that will imply it is the maximal connected component containing identity in G of A. Now we can see some examples. So take two very common examples of Banach algebra, A to B, C of X, and A to B, B of H. In C of X, X is a compact Hausdorff space. In C of X, my identity is the constant map 1. And in B of H, my identity is the identity operator. In C of X, G of A is the set of all maps that do not take the value 0 on the domain. And in B of H, all the invertible elements are those which are bijected. Okay, so now let's talk about G1 of X. So if I take C of X and X to be D, the open unit disk, then one can use the fact that the open unit disk is convex and show that in this case G1 of A will be nothing but G of A. It uses the fact that D is convex. You can try and show this, and if I take X to be the unit circle, then G1 of A is not equal to G of A because you have this map f of z is equal to z. It belongs to G of A, but there does not exist a G belonging to C of t such that I can write f is equal to exponential of G. So you can also take this. This is a fact which depends on the Wiener number, winding number of the function f. And when I come to B of H, if I take my A to be mn of C, you know that G ln of C is connected. Hence, G1 of A is equal to G of A in this case. And even for B of H, G1 of A is equal to G of A, you can use it. You can show it by using the polar decomposition of an invertible element in B of H. So this was just a short introduction to the connected component of G of A containing the identity. Next is sigma A, which denotes the spectrum of an element. S of A will denote the set of all self-adjoint elements in a C-star algebra. And mod A denotes the square root of the positive element A star A in a C-star algebra. What do I mean by a character on a Banach algebra? A map from a Banach algebra A to C, which is both linear and multiplicative, will be called a character. Now I come to the first main theorem of the talk, which is the Jason-Kahane-Zarasko theorem. It characterizes all characters on a unital Banach algebra. It says that if I have a map phi from A to C, which is linear and which satisfies this condition, that is phi of A belongs to the spectrum of A for each A, then phi will be a character. That is, if phi is linear and if it satisfies this property, it will become multiplicative too. Next, what is Kowalski and Slotkovsky, they gave a generalization to the GK theorem. What they did is they removed the notion, the criteria of linearity from the hypothesis, and they gave a similar result without assuming linearity. So they proved that if I have a map from A to C, not assumed to be linear, such that phi of 0 is equal to 0 and phi of A plus phi of B belongs to the spectrum of A and B for each AB, then phi is the character. So without assuming linearity and with taking this condition, they proved that phi is both linear and multiplicative. Now the question of the day is, can we talk about a multiplicative version of the Kowalski-Slotkovsky theorem? That is, if I take a map and in this condition, if I replace addition with multiplication, will I get the same result? So this is the statement. If A is the Banach algebra and phi A to C is a map, such that phi A into phi B belongs to the spectrum of AB for all AB, will phi be a character? Using just this condition, can I prove that phi is both linear and multiplicative? So at the face of it, it is not true. You can show it by an easy example. Considering A is equal to C2, with pointwise multiplication in any algebra norm, it will become a C-star algebra. Define this map. Phi alpha beta is equal to beta if alpha is not equal to 0 and 0 if alpha is equal to 0. You can take this map and you can prove that phi of A and phi of B belongs to the spectrum of AB. You can also show that phi is multiplicative. One can show that phi is homogeneous, but phi is not linear. Because if you see phi of 1, 1 plus phi of minus 1, 1, this is equal to 1 plus 1, but this is not equal to phi of 0, 1, because phi of 0, 1 is going to be 0. Okay? One can also note that this map is not continuous, because if I take the sequence 1 by n 0 in this case, it converges to, 1 by n 1, it converges to 0, 1. But phi of 1 by n 1, it is going to be 1 for each n, but phi of 0, 1, this is 0. Hence this map is not continuous. So this is an observation that we got a counter example, but the map was not continuous. So it seems reasonable to add continuity to our assumption of the result that we want to prove. So the final question is, if A is a unital C-star algebra and phi A to C is a function satisfying these properties, P1, P2 and P3, then we have proved that phi is both linear and multiplicative. So the rest of the talk is going to be about how we actually prove this theorem. So I'll just write what is P1, P2, P3 on the board. So we'll just keep it here on the board for throughout the talk. When a map satisfies the conditions P1 and P2, we call it multiplicatively spectral function, hence the title of the talk, characterization of multiplicatively spectral functions. Okay, so before we published our result, our co-authors, they looked at the same problems, but in a previous paper, they gave partial results to the problem, and in this current paper, we extended it to the whole Banach algebra. So let us take a look at those results which were given by them before. So in this paper, some character generating functions on the Banach algebra, our co-authors gave this result. So if phi is a continuous multiplicatively spectral function, that means phi satisfies all P1, P2 and P3. Then they prove that if x is self-adjoint, then phi of lambda, phi of e raised to power lambda x is e raised to power lambda. And if x1, x2, xn are self-adjoint elements, then phi of the product of exponentials is the product of the phi of the exponentials. And if x and y are self-adjoint, then phi of x plus y is equal to phi of x plus phi of y. So you can see here that phi behaves nicely with self-adjoint element, and this is a typical element from G1 of A. So phi is behaving nicely on G1 of A too. Next, what they do is, given any element in a C-star algebra, you can decompose it into its real and imaginary parts. And both the real and imaginary parts are self-adjoint. So what they did is, using the real and imaginary parts of an element, they defined a new function. So you have given a phi which satisfies P1, P2 and P3. They defined a new function xi phi, which is phi rx plus I phi ix. For each x it is defined like this. What they proved is, even if it is not given that phi is a character, xi phi which they have defined is going to be a character. It is going to be linear and multiplicative on the given C-star algebra. Further, the most important thing and the last result that is showed in this paper, the partial result, is that phi and xi phi coincide on G of A union S of A. So, phi and xi phi coincide on this subset of the C-star algebra. What we want to do is see that phi and xi phi coincide on the whole C-star algebra. So, we will take this result here. So, to prove that, so since xi phi is a character, if I show that it is equal to phi on the whole C-star algebra, phi also becomes a character. So, how we prove this includes a series of lemmas. So, I will list and I will try to prove a few of the results so that you can see how the properties P1, P2 and P3 are used to arrive at our final result. Okay, so this is the list of first lemmas. I am not going to read them out. Let me go to lemma number 4 and then we'll come back to this to see how these three lemmas have been used. Okay, so I have this very important lemma. So if phi is a continuous multiplicative spectral function on a C-star algebra, that is if phi satisfies P1, P2 and P3, if I have an x such that xi phi of x is equal to 0, then phi will also become 0 at that point. Okay, so let us see how that is proved. Okay, so are you able to see these both? Okay. So I start with an x. So x given belong to x. I am given that xi phi of x is equal to 0. Now x is rx plus ix. I just remove the subscript rx here. It is r plus I. Xi phi of x is given to be 0. This will imply xi phi of r is equal to 0 and xi phi of I is equal to 0 because xi phi is a character. Okay. Now r and I are self-adjoint elements. I can talk about mod r and mod I. They are positive elements. Further, I can talk about mod r square and mod I square. They are also positive. Sum of two positive elements in the C-star algebra is again positive. So mod r square plus mod I square is positive. Okay? And I can also consider okay. Now consider for each n the element e raised to power minus n root of mod r square plus mod I square. This element here is positive. Do you agree that this element for each n is positive? So this will also be positive. Now, so that is, in particular, it is self-adjoint. So they had proved before that phi and xi phi coincide on the self-adjoint elements. So phi of Wn is equal to xi phi of Wn. Since phi is linear and multiplicative, using the fact that xi phi is linear and multiplicative, this xi phi will straight go inside. Okay. And what did I have? Xi phi r and xi phi r are 0. So this is e raised to power minus n0, which is 1. Okay. So now coming back to phi of x, I wanted to show that this phi of x is 0. Phi of x is nothing but phi of x dot 1. Instead of 1, I can write phi of Wn is equal to phi of x dot phi of Wn. Now what can I use? I can use P1. This means this belongs to the spectrum of x Wn. Now phi of x belongs to the spectrum of x Wn. That means mod phi of x is less than equal to norm x Wn. Okay, if I show as n tends to infinity, this value goes to 0, I will get phi of x is equal to 0. So now I will use these weird looking lemmas here. Okay, so lemma 3, I have that this element here is positive and hence self-adjoint. Hence by lemma 3, limit root mod r square plus mod I square e raised to power minus n root mod r square plus mod I square is equal to 0. Then I go to lemma 2. Since mod r square is less than equal to mod r square plus mod I square, so a square is less than equal to b square. If limit b bn is equal to 0 will imply limit a bn is equal to 0. So by lemma 2 I will get limit n mod r e raised to minus n root mod r square plus mod I square is equal to 0. Then I go to lemma 2. If limit n mod a bn is equal to 0, then limit n a bn is equal to 0. So, here it is 1. Similarly, I can show that limit I e raised to power minus n, this value is equal to 0. And adding both, I will get that limit x e raised to power n, this is equal to 0. That is limit n x wn is equal to 0, which is what I wanted. If I put it here, I will get mod phi of x is equal to 0, and hence phi of x is equal to 0. So this is how I use the 3 lemmas and my 3 properties P1, P2 and P3. Now my next aim is that if belongs to x and xi phi of x is equal to 0. I have shown that this implies phi of x is equal to 0. What I want to show is phi of alpha 1 plus x is equal to alpha for all alpha belonging to C. So if I have an element x such that xi phi of x is equal to 0, I want to show that phi of alpha 1 plus x is equal to alpha for all alpha belonging to C. If I prove this, then I am done. If you see, I just have to use a small trick and I will be done. So to get this result also there were a bit of stages. So first we proved that if this holds, if at a point xi phi of x is equal to 0, first we got that phi of alpha 1 plus x is equal to C alpha for some C alpha belong to 0, 1. So this was partial. Next we made some improvement where the C alpha instead of belonging to the closed interval 0, 1, we brought it down to C alpha belonging to the set containing 0 or 1. Okay, so at this point phi of alpha 1 plus x is equal to alpha or 0. That means phi of alpha 1 plus x can be 0 for a non-zero alpha also at this stage. Okay, so now just in my last computation we will show you how we moved from that stage to the last. So x belong to x, given that xi phi of x is equal to 0, that is phi of x is equal to 0 by lemma 4, to show phi of alpha 1 plus x is equal to 0 for all alpha belonging to C. Okay, so I have phi of alpha 1 plus x is equal to C alpha where C alpha belongs to 0 or 1. I want to show, okay, so now consider this set K of x is equal to alpha belonging to C such that phi of alpha 1 plus x is equal to 0. At this point of 6, this can contain non-zero complex numbers. My aim is to show that Kx is a singleton 0. Okay, to show K of x is the singleton 0. Now, do you agree that K of x is a closed set? It is the inverse image of 0 under a continuous map. So here I use the fact that phi is continuous. Okay, so K of x is closed. K of x is non-empty. It is non-empty because 0 belongs to K of x. Okay. Next, is K of x bounded? Okay, so let alpha belong to K of x, that is phi of alpha 1 plus x is equal to 0 belongs to the spectrum of alpha 1 plus x. Okay, that is 0 belongs to the spectrum of alpha 1 plus x, that is minus alpha belongs to the spectrum of x. So that is mod alpha is less than equal to norm x. So every element in K of x is bounded by norm x, hence K of x is bounded. So I can say that K of x is compact. Now since K of x is compact, there exists a alpha naught belonging to K of x such that mod alpha naught is greater than equal to mod alpha for all alpha belonging to K of x. I have an element with the maximum modulus, and this element with the maximum modulus will lie on the boundary of K of x. So if you imagine K of x to be something like this, you have alpha naught here. I have now, so this is K of x. x. I will have some element, sequence of elements, alpha n belonging to k of x complement, which converge to alpha naught. Okay? Now, what is going to be phi alpha n plus x? They belong to k of x complement. This is going to be 0 for all n, but this converges to phi of alpha naught plus x, which is alpha naught. So by uniqueness of limit, my alpha naught is nothing but 0. So the element with the maximum modulus is the 0 element in this set. Hence my k of x is the set 0. So I have proved that phi of alpha 1 plus x is equal to 0 for all alpha belong to C if xi phi of x is equal to 0. Now my final step is just one trick. So I start with phi of x. I can write it as phi of xi phi of x plus x minus xi phi of x. Take this to be your alpha and this to be the element where xi phi of x vanishes. This will become xi phi of x. Hence phi of x and xi phi of x will coincide on the whole C star algebra. So this is just showed you. So one can see that I do not in my hypothesis phi of 1 to be equal to 1 because P1 says that phi of 1 the whole square belongs to the spectrum of 1, that is phi of 1 square is equal to 1, that is phi of 1 is either 1 or minus 1. So I can use this whole process because then phi of 1 is equal to 1 or minus phi is equal to 1. So the whole process I can use for either phi or minus phi. So if I remove the condition P2, I can say that phi or minus phi is a character on A. I can extend this result to maps between A and B where B is a commutative C star algebra. So here the trick is, this is also easy. This is a very standard procedure when you want to extend such results to between spaces instead of A to C. So take any phi belonging to the maximal ideal space of B and consider phi composition T. Then phi composition T is a map from A to C. See if it satisfies P1, P2 and P3 and you can get this result here. That's it. So that was all about my talk. Thank you for your patience.
Thank you very much for your talk. Are there questions, remarks? This seems not the case. Thank you very much again.
I invite the chair to present a token of appreciation to the speaker.
Thank you.
Now we will be having a tea break. We will be starting our next session by sharp 10:45.